These aren't stars, they never were. For nearly 4 years, the James Webb Space Telescope has been staring deep into the early universe, peeling back the layers of time. It is looking at light that left its source over 13 billion years ago. And in that ancient darkness, Webb has been finding something nobody can explain. Tiny, red, glowing objects, hundreds of them, thousands. They have the shape of stars, the color of stars, even the brightness profile of stars. But the spectra tell a different story. A story so disturbing that some of the smartest astronomers alive right now are starting to whisper a single word about them. Not stars, black holes. Black holes wearing stars like a costume, and they appear to be multiplying. The worst part isn't that we found them. The worst part is what they imply about how the universe actually built itself. Because if these things are what we think they are, then everything we believed about how the first supermassive black holes formed was wrong. Not slightly wrong, catastrophically wrong. By the end, you'll understand why a population of strange red specks at the edge of the visible universe might be the most important discovery Webb has made so far. And we'll come back to one number near the end that changes the entire picture. Start with what we thought we knew. For decades, the standard picture of the early universe went something like this. After the Big Bang, hydrogen and helium gas slowly collected into clumps. Those clumps collapsed into the first stars, massive things, hundreds of times heavier than our sun, burning hot and fast. When they died, some of them left behind small black holes. Those black holes ate matter, merged with other black holes, grew over hundreds of millions of years, and eventually became the supermassive monsters at the centers of galaxies. Clean, orderly, slow. The problem is that the universe didn't get the memo. As far back as we can see, less than 1 billion years after the Big Bang, there are already supermassive black holes. Some weigh in at billions of times the mass of our sun. Billions. That is not enough time to grow one through normal feeding. It would be like finding out a kid started kindergarten yesterday and is already 6.5 feet tall, fluent in 4 languages, and married. Something is missing from our story. Something big. Enter James Webb. When it launched in late 2021 and started returning real data the following summer, astronomers expected confirmation of the existing model. They expected to see the first galaxies forming slowly, gently, in a universe still cooling off from its violent birth. What they got instead was a flood of objects that should not have existed yet. Massive galaxies, fully formed, only a few 100 million years after the Big Bang. Bright quasars, where the math said quasars couldn't yet exist. And, scattered through the data like a virus, these little red dots. Compact, reddish, tiny on the sky, but undeniable in number. At first, nobody knew what to make of them. The dots showed up in survey after survey, in different patches of the sky, with the same properties. They were small, no bigger than a few hundred light-years across in many cases, which is incredibly compact by galactic standards. Our own Milky Way, by comparison, is around 100,000 light-years wide. These dots were like trying to spot a single neighborhood from the other side of the country. They were red, which usually means dust, or distance, or age. And they were everywhere. By 2023, researchers including Dale Kosevsky at Colby College and Jorrit Matthey at the Institute of Science and Technology Austria were publishing papers on these objects. Their finding, the dots made up around 1% of galaxies in the early universe. 1 in 100. At those distances, that is an enormous fraction. So a question that should bother you: what are they actually made of? The first guess was the natural one. They're galaxies. Dusty, dim, ordinary galaxies, seen through enough distance to redden them out. That explanation lasted about a year. Then someone actually pointed Webb's spectrographs at the dots and looked at the chemical fingerprints of their light. What came back wasn't the signature of a quiet, dust-choked galaxy. It was something stranger. The spectra showed extremely broad emission lines, specifically broad hydrogen lines, the one called H-alpha. In astronomy, broad means fast. When gas is moving toward you and away from you at thousands of miles per second, the light it gives off gets smeared. It spreads across a wide range of wavelengths instead of arriving as a single sharp line. That kind of motion does not happen inside ordinary stars. It does not happen in calm galactic interiors. It happens in exactly one place, the inner edge of a black hole's accretion disk, where matter is spiraling inward at relativistic speeds before it disappears forever.
The little red dots were screaming with a spectral voice of feeding black holes. And not little ones either. The math suggested black holes of around 1 million solar masses, sometimes more. 1 million suns of mass crammed into a region smaller than our solar system, and sitting at the heart of an object so compact and so red that for years we thought it was just a dim, ordinary star far away. And there are not a handful of these. There are thousands, spread across the early universe, like seeds of something we don't fully understand yet. And the numbers don't add up. The amount of light coming from these objects, paired with the velocities in their spectra, leads to a paradox. These would be black holes that are too big, in objects that are too small, in a universe that is too young. Roberto Maialino at Cambridge and other researchers have been chewing on this problem for years, and one hypothesis keeps surviving the data. The little red dots may not be black holes inside galaxies in the way we normally picture them. They may be something else entirely. A type of object that was theorized in the 2000s, almost dismissed as a curiosity, and is now staging the most unlikely comeback in modern astronomy. They may be black hole stars. Hold on to that phrase, because it sounds like science fiction, and it is not. The technical term is quasi-star. The idea, first laid out in detail by Mitchell Beagleman and his colleagues in the mid-2000s, goes like this. In the early universe, a very large cloud of gas collapses. If that collapse happens fast enough and doesn't fragment into many small stars, the very center can keep collapsing past every stopping point. It falls directly into a black hole. The rest of the gas cloud, though, doesn't go with it. The outer layers, hundreds of thousands of times the mass of the Sun, stay puffed up around the new black hole. They're held in place by the heat and radiation from material falling in. From the outside, you would see what looks like a single, enormous glowing object, a star. From the inside, you would have a black hole feeding on the body it lives in. Picture a planet with a swarm of bees at its core. The bees are eating the planet from the middle outward, and the planet keeps shining because of the violence happening at its heart. The whole thing isn't bound together by ordinary stellar physics. It holds itself up through a balance between gravity pulling inward and radiation from the central black hole pushing outward. It is, in every way that matters, a star with a monster inside of it. And it grows fast. A normal star like our Sun took millions of years to form and will live for about 10 billion years. A quasi-star could form in less than 1 million years. The black hole at its center can grow at rates that ordinary naked black holes simply cannot achieve, because the black hole is wrapped in its own food source. Fuel never runs out. It eats until the envelope can no longer hold itself up, at which point the whole structure collapses. What gets left behind is a much larger black hole than anything normal stellar evolution could create. Maybe 100,000 solar masses in a single shot. That black hole, born already monstrous, becomes the seed for a future supermassive black hole. And the rest of the early universe is full of those seeds. Stand on the surface of one of these things for a moment, or rather, try to. There is no surface in the normal sense. You're sitting on a layer of glowing hydrogen and helium, hundreds of millions of miles above a hole in space that is consuming everything beneath you. The light around you is coming from gas that is being shredded just out of sight. The pressure under your feet is the radiation of an entire small galaxy's worth of luminosity, compressed into a single object. You would not survive a millisecond. But if you could watch, you would see the most violent thing in the early universe, hidden inside a deceptive softness. A red, glowing ball. From a billion light years away, you might mistake it for a star. Webb did. Now back to the data, because the picture I just described, a quasi-star sitting at the heart of every little red dot, is one hypothesis. Not the only one. Other researchers argue the dots are simply early-stage, active galactic nuclei, normal accreting black holes, with their host galaxies obscured by dust. Still others suggest they could be a kind of object that doesn't have a clean name yet, somewhere between a stellar cluster and a feeding black hole. The arguments are fierce, and the papers are coming out faster than the field can absorb them. What everyone agrees on is that the dots are not acting like ordinary galaxies. The disagreement is about exactly what they are doing wrong.
The dots are also doing one more thing. They are multiplying. I don't mean they are breeding, they are not alive. I mean that every time Webb looks at a new patch of the early universe, it finds more of them. The deeper the survey, the more dots. The more carefully the spectra are analyzed, the more of them turn out to have those broad emission lines. Estimates of their abundance keep climbing. Early counts said maybe a few hundred existed in the volumes Webb could see. Updated counts suggest tens of thousands. Some researchers now suspect something striking. From about 500 million years to a billion years after the Big Bang, the little red dots may have been the dominant population of accreting black holes. Not the rare exception, the rule itself. If that's true, the implications are hard to overstate. It means that for years, when we counted galaxies in the early universe, we were also counting black hole stars without realizing it. It means the number of black holes in the early universe is far higher than anyone calculated. And it means the formation of supermassive black holes was not a slow grind starting from stellar remnants. It was a flash flood. A burst of giant seed black holes, born already enormous, hidden inside glowing envelopes, all over the place at the same time. That changes the chicken and egg problem we mentioned earlier. For decades, astronomers have argued about what came first, galaxies or the supermassive black holes at their centers. The universe is full of evidence that the two are linked. The mass of a central black hole tends to scale neatly with the mass of the host galaxy's bulge. Something tied them together early. If the little red dots are the missing seeds, then the answer is that the black holes did not grow alongside their galaxies. They came first, fully formed, monsters already, and then drew material toward them to build the rest. The galaxies grew around the black holes, not the other way around. In some recent analyses of high redshift galaxies, roughly a third of the brightest objects in the sample show signs of being little red dots. That means a similar fraction of the earliest galaxies were black hole-dominated objects, not stellar-dominated ones. Take that number to its conclusion. Almost a third of the brightest objects from that early era may be sitting on top of monstrous, mostly hidden black holes. The early universe in this picture isn't a dim sea of new stars sparkling into life. It's a graveyard of giants in disguise. Caleb Scharf, an astrobiologist and writer who has been thinking about these objects for years, has pointed out something else worth sitting with. If quasi-stars really did dominate the early universe, then the conditions for life as we understand it would have been profoundly different than what we usually imagine. The first billion years wasn't quiet starlight. It was the screaming output of seed black holes wrapped in shrouds of gas, blasting radiation in every direction, sterilizing volumes of space the size of small galaxies. The universe didn't begin gently. It began with predators already at the table. And if these black hole stars existed in the early universe, the question becomes, where are they now? The straightforward answer is that they ended. Their envelopes collapsed, their black holes fell quiet for a while. Over billions of years, those naked seed black holes grew, merged, and became the supermassive monsters at the cores of present-day galaxies, including ours. Sagittarius A star is the 4 million solar mass black hole at the center of the Milky Way. It may be a descendant of a quasi-star that existed when the universe was less than 1 billion years old. Our galaxy may have inherited it. That makes Sagittarius A star less mysterious in one sense and far more disturbing in another. Less mysterious because we have a possible origin story. More disturbing because the origin story is, at its root, an object that nobody fully understands yet. A black hole that lived inside a star, ate its way out, and then waited while a galaxy formed around it. The Milky Way may be the slow afterimage of a death we never witnessed. And there's the number I told you I'd come back to. The little red dot population suggests that the universe may have produced something on the order of 100 million seed black holes during its first billion years. 100 million. That kind of seed population would solve a problem astronomers have wrestled with for decades. The supermassive black holes we see in the most distant quasars don't have time to grow from small stellar remnants alone. If even a fraction of them grew from quasi-star seeds instead, the timeline finally starts to work. We didn't find a missing piece of the puzzle. We found a piece we didn't know was missing. Of finding objects fainter than the original surveys planned for, and deep field campaigns ahead will push these observations even further into the early universe. New spectroscopic studies will try to break the ambiguity. If a dot is a quasi-star, its spectrum should look slightly different from a dust-shrouded galaxy or a naked, accreting black hole. The differences are subtle. The data will need years of patient work. But the answers are coming. The community is not going to leave this one open. In the meantime, the consequences of even partial confirmation are already rippling through the field. Models of galaxy formation are being rewritten. Predictions for what the next generation of telescopes will see are being adjusted. The Vera C. Rubin Observatory, the Square Kilometer Array, and the extremely large telescope now under construction in Chile will all be hunting for follow-up signatures of these objects. They'll search for the unique radio and X-ray fingerprints these things would leave behind. We are not just discovering little red dots. We are discovering a phase of the universe's history that we did not know existed. Step back for a moment. Forget the technical details. Think about what it means that for 13 billion years, the universe was hiding something. Something that, by any reasonable accounting, should have been one of the most obvious features of the early universe. Black holes the size of small galaxies, glowing red in the early dark, multiplying by the thousands across a young universe. And we missed them. They were there the whole time. We just didn't have eyes good enough to see them clearly. Every telescope before Webb was looking at the same patch of sky, and either ignored these objects or misclassified them. What else are we missing? That question is not rhetorical. The history of astronomy is, in large part, a history of being humbled by your own assumptions. We thought the Milky Way was the universe until 1924. We thought the universe was static until 1929. We thought the cosmic background radiation was noise until 1964. Every time we built a better instrument, we discovered that what we thought we understood was a small slice of a much larger and stranger reality. Webb is doing that again, right now. And what it is showing us is that the early universe was populated by things we don't have good names for yet. The little red dots may eventually turn out to be something more mundane than black hole stars. The hypothesis could collapse, and other explanations could prevail. But even in that case, the existence of these objects tells us, beyond any doubt, that the earliest era of the universe was not what we expected. It was more violent, more crowded, and stranger than anything our models predicted. And our models had been calibrated for decades. A different angle. Most of the matter in those distant red dots, if they are quasi-stars, is going down a drain that has no bottom. The light we see from them is the last cry of gas being shredded as it falls in. Every photon Webb collects from a little red dot is, in effect, a goodbye. A piece of the early universe saying, "This is the last thing I will ever shine before the dark takes me." Multiply that by tens of thousands of dots. What you have is a portrait of a universe in the act of devouring itself, slowly, calmly, while looking from the outside like a sea of red stars. We thought the cosmic dawn was about birth. It might have been about feeding, on a scale we are only now beginning to grasp. The universe didn't wake up gently in the first billion years. It woke up hungry. And the proof is sitting in the data right now. On hard drives in Baltimore and Heidelberg and Cambridge, a quiet population of red dots has been multiplying in our images and in our understanding since Webb opened its eyes. Webb didn't just see deeper than every telescope before it. It saw something the others were missing, hiding in plain sight the entire time. And that's it for this video. Thanks for watching, and I'll see you in the next one.